Okay, so let's use this one. And then let's go over these three cases one more time. All right, so case number one. Okay, guys, what's the angle between this force and this displacement? It's going to be 0 degrees, right? All right, so what is the cosine of 0?
1.
It's going to be 1. Okay, so if that's the case, what do we get? It's going to be positive work. All right, so it's going to be FR cosine of 0. It's going to be 1. So it's going to be positive work. You end up getting a positive result. All right, so case number 2, which is this. What's the angle between these two? It's going to be 180 degrees, right? All right, so the cosine of 180 degrees is going to be -1. So WFR cosine of 180 degrees is going to be negative delta E. Okay, because this thing is going to be negative. It's going to be -1. Okay, so case number 3. If the angle is 90 degrees, what do we get? Cosine of 90 is going to be 0, right? So it's going to be FR cosine of 90 degrees. Okay, so this is going to be 0. So delta E is going to be 0. So no energy is being transferred. Okay, so this is the first case, which is the same as this. Here's the second case, which is the same as this. And when it's 90 degrees, cosine of 90 is going to be 0, so that's the third case. Okay, so it worked out nicely. Okay, so problems. Okay, so the numbers are a little bit made up, but let's go forward. Okay, so the formatted solution sheet. Okay, it's 7:26. All right, guys, let's go take a break and then we'll continue. Take a break for 10. Okay, so problem number 3. Okay, guys, evidently this problem is slightly made up. Okay, so this Alexev guy is lifting 562 pounds. So that one is accurate. Over 2 meters, that's also accurate. Paul Anderson is not lifting 6,270 pounds. It's more like 2,400 pounds. But let's go with these numbers. Okay, so what do we know? I'm going to have the Russian on the left. And I'm going to have the American on the right. All right, so let's just left. That's not left. Okay, it's gonna look like this. So both of them are gonna be applying a force on something. This thing is gonna have weight. The amount of applied force is simply gonna match the weight in this direction. So both of them will apply a force on the y direction, and both of them will cause a displacement in this direction. And in this case, this is gonna be mg. So just remember that. So it's not work; it's just the weight. Okay, so the amount of force that the Alexev is going to apply is going to be 562 pounds. So we got it from here. Okay, so Anderson is going to be 6,270. Okay, so in the case of Alexev, he's going to be lifting it over 6 feet. And Anderson is going to be 1 centimeter. It's like half an inch. Okay, so what else do we have? Okay, so what is the amount of work that these people do in terms of joules and also in terms of kilocalories? All right, so that's what we want to figure out. Okay, so I've done the conversions already. So the force in this case is going to be 2,554.54 newtons. Here it's going to be 28,500 newtons. That's what we got. Okay, so we're done with the conversions. Okay, so the amount of work done. How do we do the amount of work done in this case? Okay, so the work is going to be, guys, it's right here. It's force times displacement. Okay, the cosine of the angle is going to be 0. So the cosine of the angle being 0, this term is going to be 0. So force times displacement. So the work done in either case is going to be force on the y direction times displacement on the y direction. So it's going to be the same. So it's a single formula. We don't have to do any work. And we will apply the same formula to both cases. That's all we have to do. Straightforward. All right, so in the case of Alexev, we're going to end up getting a number. And in the case of Anderson, we're going to end up getting a different number. Okay, so what do we have in the case of Alexev? The force is going to be this number times 6 feet, which is going to be a displacement. All right, so what is 6 feet? No, it's not 6 feet. What is it? Is it 2 meters? Okay, I messed it up. So that should have been 2 meters. All right, so this is 2 meters. All right, so the distance is already given in terms of meters. And 1 centimeter is going to be 100th of a meter. Okay, so we got that one. Okay, so those are the only conversions we got. Okay, so this times that is going to be the amount of work. And in the case of Anderson, this is going to be 28,000 newtons times this number. All right, so we'll get the answers in terms of joules. All right, so this is going to be 5,109.08. And the other one is going to be 282. Okay, this one is going to be 285 joules. Okay, so the conversion factor, this is a conversion exercise. All right, so both of them will get multiplied by the conversion factor. Okay, so let's go from joules to calories. 1 kilocalorie is going to be 4,186 joules. So the guy on the left, the amount of work that he does is going to be 1.22 calories or kilocalories. All right, so this is for Alexev, and for Anderson, it's going to be 0.07 calories of work. Okay, so which one is more difficult? All right, if you take a look at the ratio, if you take a look at this and divide it by this, it's going to give you the ratio. This divided by that is going to give you a ratio which is 17.5 times. Okay, so lifting 600 pounds over 6 feet is going to be 17.5 times more difficult than lifting 6,000 pounds, something which is about 6,000 pounds over half an inch. Okay, so that's what it means. Okay, so what that means is, okay, guys, so this is the amount of work that he does, the amount of energy that he transfers, the amount of work that he does is going to be 1.22 calories of work. The amount of work that this guy does, if he's lifting 6,207 pounds, 70 pounds, this is 0.07, 700th of a calorie of work being done. So the lifting 600 pounds over 6 feet is going to be 17.5 times more difficult than lifting 6,000 pounds less than an inch. That's what it means. This is the reason why this is an Olympic sport and this is a freak sideshow. Okay, so that's the reason why. Okay, very good. Give yourself 5 points, Corona. Okay. All right, so she's got the, or he's got the right answer. All right. So this is a lot more difficult than this one. So you guys kind of guessed it correctly. So those of you guys who guessed it correctly, give yourself 20 points for that one. Okay, so the question is, just imagine that 600 pounds and these people weigh 6,000 pounds. Okay, so the question is, why is it lifting something 600 pounds over 6 feet, something which is 10 times lighter, is going to be a lot more work than lifting something 10 times heavier? Okay, so what's the reason for it? Guys, this is 10 times lighter, but the distance lifted, displacement is much, much larger. And if you're lifting something over 6 feet, right, this is 1 centimeter, this is like 200 times larger. Distance, okay, this is 10 times lighter, but the distance is 200 times larger. The distance being lifted here. Okay, so this one is 10 times heavier. The distance is 1/200th of a distance that this guy is lifting. Okay, so that's the reason why. So this one is a lot more work than the other one is. Okay, so this brings us to the next point. The next point is the work energy theorem. You know that the work is a process of transferring energy, right? So the amount of energy that you transfer depends on the amount of work that you do. So in this case, we're lifting something up. Whenever you're lifting something up, oh my God, this is going to be a lot of work. Okay, guys, so I got this, I'm lifting it up. Okay, so I apply a force on it. So it's going to get displaced in the direction of the force, right? All right, so the force and displacement, they're in the same direction, so which means that the energy is being transferred to the object that I'm lifting. All right, so the amount of energy that I transfer is the amount of energy that gets stored in this object. So that's known as the potential energy. So by lifting something up, you transfer energy to the object. So the amount of energy that you transfer is going to become stored in that object. Okay. So we're lifting something up against gravity. This is a key term that I want you to remember. Okay. So whenever you do work against gravity, by lifting something up, the amount of work that you do is going to go into the energy of this object, which means that the amount of work that you do is going to become stored in that object, which is known as potential energy. Potential energy simply means stored energy. That's what it means. All right, so by lifting something up, we end up storing energy in that object. All right, so the next topic is the potential energy. All right, so by lifting something up.
You're still in the PowerPoint.
Yeah, I was just about to say that.
Okay, am I still in PowerPoint? Are you guys able to see this?
We can see you now.
Okay, cool. Give yourselves 5 points for saying it. All right, so the potential energy is the amount of work that you do in lifting something up against gravity. All right, so I'm displacing it along this direction by applying a force on it along the same direction, and it's got mass. All right, so the amount of work that I do in lifting something up is going to go into the potential energy of the subject. All right, so this is otherwise known as potential energy. mg times the height. All right, so the amount of energy that you store is going to depend on the displacement, the height. Okay, and then this is the amount of work that you do against gravity. It also depends on the mass. Okay, so that's the amount of energy that object has by virtue of its position with displacement with respect to the ground in this case. All right, so P is your potential energy. M is the mass. Well, we know what G is, so roughly about 10 meters per second squared. And this is your displacement. In this case, it's the height. This is going to be in terms of meters, kilograms, joules. So that's what we got. All right, so we got the potential energy. It's going to be related to height. Okay, so potential energy is going to be related to height. All right, so we got the ball. It's got potential energy, right? All right, so potential energy also depends on the height with respect to our reference point. Okay, so we're going to be looking at potential energy with respect to this point, this height. Okay, so it depends on the difference in height that we're looking at. That's the amount of potential energy which is going to be stored. Okay, so what happens is when you let the ball go, potential energy is going to go down, right? Because the height goes down. All right, so as the distance diminishes, the potential energy is going to diminish. It strictly depends on the height. So potential energy strictly depends on the height. So whenever you let a ball go, all right, so what happens is gravity is going to take over. And as the distance starts to go down, the potential energy is going to go down. Messed it up. Potential energy is going to go down. When you increase the distance, potential energy is going to go up. So potential energy depends on the distance for a given mass. All right, so the distance goes up, potential energy goes up. Distance goes down, potential energy goes down. Okay, so potential energy depends on the height, it depends on the position.